Integrating voice assistant (VA) features into mobile applications is crucial for enhancing usability, but it poses a significant challenge for developers. To address this, Test2VA presents a novel approach that reuses GUI test code to automatically generate functional code supporting VA task execution. By repurposing GUI test scripts for VA tasks, Test2VA aims to reduce the workload and improve code efficiency. The proposed method involves identifying mutable GUI events within test cases and parameterizing them in VA methods. An evaluation of 48 test cases from 8 real-world applications demonstrated the effectiveness of this approach, with 75.68% of mutable events successfully detected and 33 VA methods generated. Manual examination of these methods confirmed their efficacy. The need for developer-oriented support to simplify and speed up VA development is increasingly important, particularly considering the growing demand for custom VA embedding in mobile apps. GUI testing, a standard procedure in application development, can be leveraged to generate VA code without introducing additional workload. This approach not only reduces the development burden on developers but also ensures the maintainability of VA code through regeneration from updated test scripts. By reusing existing GUI test code, Test2VA offers a promising solution to facilitate the integration of VA features in mobile applications, addressing the challenges faced by developers and promoting efficient VA development. In their research paper, authors Garrett Weaver and Shui Chin introduce a novel approach called Test2VA, which automates the development of customized voice assistant features for mobile applications. This system utilizes the application's GUI test scripts and consists of 3 components: a parser, a dynamic detector, and a generator. The parser interprets the original GUI test script into a sequence of event notations, while the detector runs the original events, replacing them with mutant event candidates and monitoring the success of task completion. The generator builds voice assistant methods based on detection results. The authors evaluate Test2VA on 48 test tasks from 8 Android applications, demonstrating that the tool can successfully detect 79.41% of mutable events in less than a minute per event and generate 33 flawless voice assistant methods. The proposed selection algorithm reduces the number of mutant event candidates by 93.31%. The paper provides background knowledge on GUI testing and GUI hierarchy, explaining that GUI events consist of GUI elements and GUI controls. It introduces the concept of mutant GUI events, which involves making small changes to the original GUI event to create multiple versions of the GUI event sequence. The research contributes to the field by exploring the potential of reusing test code for non-testing purposes, proposing a novel approach to automate voice assistant feature development, and evaluating the tool on real-world applications. The authors also discuss potential flaws in the generated methods and provide an in-depth failure categorization. The authors introduce Test2VA, a methodology that reuses GUI test cases to develop voice assistant features in mobile applications. In voice assistants like Alexa, natural language processing (NLP) identifies the most likely skill to execute a user's command, invoking the working code of the matched skill to perform the requested task, which may require parameters to indicate specific details. The authors illustrate this concept using an Android application, another Notes app, which demonstrates how GUI test scripts can be reused to develop voice assistant features. Customized app functions are defined as tasks, achieved through interactions between applications and app users, visually represented on application screens and within the testing code. For example, a setup task sets up a swipe left action to delete a note. This task can be automated in a GUI testing step by step using a testing framework like Espresso. The GUI test script records interactions between the user and the application, including finding view interaction objects and performing actions like clicking and asserting whether the test result matches the expected behavior. By abstracting the task's design pattern, the authors identified 2 types of interactions: those reflecting the application's designated functionalities and those relating to the user's customized data. Non-changeable parts of the pattern represent the application's functionalities, while changeable parts represent the user's customized data. The example tasks demonstrate the feasibility of extracting the design pattern from the test code, paving the way for reusing GUI test cases to develop voice assistant features in mobile applications. The Test2VA approach is a method for reusing test code to generate task methods that support visual analytics (VA) feature development. This approach involves three major processes: test script parser, dynamic mutant detector, and task method generator. The test script parser translates test scripts into a structured notation, capturing essential information such as GUI element criteria and actions applied. This notation serves as input for the dynamic mutant detector, which dynamically re-executes every event from the original test task while replacing it with mutant event candidates. The dynamic mutant detector identifies mutable events and records new event sequences as alternative successful sequence instances if the mutant passes the assertion. This process enables the detection of multiple successful event sequences, which is crucial for generating task methods that support VA feature development. The task method generator analyzes the detector report and generates the task method. This process can be repeated multiple times to generate several methods if there is more than one test script. By reusing test code, the Test2VA approach streamlines the development of task methods, reducing the need for manual coding and increasing the efficiency of VA feature development. The Test2VA approach reuses GUI test cases for voice assistant features development in mobile applications by leveraging a mutant detection algorithm and a candidate selection algorithm. The mutant detection algorithm, outlined in Algorithm 1, takes an Appium driver and parser notation as input and outputs a pool of mutants for each event. It sets up the application, executes the base task to obtain the event sequence, and generates a pool of mutants for each target event. The algorithm iterates through each mutant, executing the event sequence, and stops execution if an error occurs. To increase the effectiveness of the detector, the candidate selection algorithm is designed to reduce the number of mutant candidates. It applies two conditions to the selector: GUI control type consistency and structural similarity. The first condition filters out mutants with different control types than the original event. The second condition selects mutants based on their structural similarity to the original event, using an XML hierarchy tree representation of the application screen. The candidate selection algorithm is illustrated through direct and indirect sibling scenarios, as shown in Figure 4. In the direct sibling scenario, mutants with similar control types and structural similarity to the original event are identified, such as the archive and none nodes as direct siblings of the event E4 node, delete. In the indirect sibling scenario, nodes with structural similarity to the original event are selected, such as the swipe right action node as an indirect sibling of the event E3 node. The Test2VA approach enables the efficient reuse of GUI test cases for voice assistant features development in mobile applications by leveraging these key components. Assertion modification is a vital concept in identifying successful mutants, defined as those that adhere to the hidden task pattern without inducing assertion failures. However, assertions may occasionally fail despite correct task completion, contingent upon their design. To address this limitation, the authors propose an assertion modification approach that updates assertion statements during dynamic task execution. When replacing original events with mutant candidates, this approach correlates textual values of GUI elements with tested values in assertions by comparing them. This correlation enables the identification of successful mutants, ensuring that assertions accurately reflect the intended task behavior. By dynamically updating assertion statements, the approach mitigates the risk of false negatives, where correct task completion is misclassified as an assertion failure. This assertion modification approach is crucial in evaluating the effectiveness of mutants, as it ensures that assertions accurately capture the intended task behavior. By refining assertion statements during dynamic task execution, the approach enhances the reliability of mutation testing, providing a more accurate assessment of software robustness. The Test2VA system reuses GUI test cases for voice assistant features development in mobile applications. It parameterizes joint textual features among GUI elements and their mutants, using an alternation event to click a different GUI element on the same screen. Additionally, Test2VA provides a service to assist the VA method execution, implementing predefined APIs in the VA method using Android Accessibility Service, which enables control of Android applications at runtime. To evaluate Test2VA, experiments were conducted on 8 open-source Android applications across different categories, aiming to answer 4 research questions. These questions concerned the success rate of Test2VA in parsing test scripts, the accuracy and efficiency of Test2VA in detecting mutants, the success rate and quality of generated task methods, and the primary causes of failure in Test2VA. The experiment setup involved selecting 8 free and open-source Android applications from the F-Droid platform, with varying app categories and versions. An Android emulator and a real Android device were used to execute the generated task methods. 6 different test cases were prepared for each application, with event sequence lengths ranging from 0 to 8, resulting in a total of 48 test cases and 163 test events. The effectiveness of the test script parser was evaluated by calculating the successful parsing rate of 8 applications for test event code and assertion code. A successful parsing was defined as meeting 3 conditions: building the parsing notation of the test case without errors, correctly reproducing the original event sequence, and passing the assertion in the original test case. The overall successful test case parsing rate was 89.58%, 43 out of 48. The impact of test sequence length on the parsing rate was analyzed, revealing that parsing rates were similar among different event length groups. The accuracy and efficiency of the mutant detector were also evaluated through 2 sets of experiments. The authors present a comprehensive evaluation of their Test2VA detector in Table 1, which lists various mobile apps, their categories, versions, and test cases used for the assessment. These test cases encompass multiple events such as creating notes, setting reminders, and searching for songs. To measure the detector's performance, the authors introduce the concept of mutable detection rate, MDR, calculated as the ratio of correctly detected mutable events to the total number of mutable events. The results of this evaluation are detailed in Table 3, demonstrating an MDR value of 75.68%, precision of 0.76, and an F1 score of 0.7. A confusion matrix is employed to calculate the F1 score and prevent the detector from labeling every event as mutable. This approach ensures a balanced evaluation of the detector's accuracy and recall. In terms of efficiency, the Test2VA detector significantly reduces the number of mutant candidates by 92.67% and requires an average time cost of 255.36 seconds per method and 67.39 seconds per event. This indicates that the detector is highly efficient in identifying and filtering out irrelevant data, thereby streamlining the analysis process. Finally, the authors assess the effectiveness of task method generation by measuring the success rate of the generated task methods. A successful method is defined as one that can reproduce the sequence of events for both the original tasks and alternative tasks with mutant events. The assertion modification algorithm successfully finds correlations on 92.5% of the methods, highlighting its efficacy in generating accurate task methods. Overall, the evaluation demonstrates the Test2VA detector's ability to accurately identify mutable events in mobile applications while maintaining high efficiency and effectiveness in task method generation. The research paper introduces Test2VA, a tool designed to automate the conversion of GUI test cases into voice assistant features for mobile applications. This section focuses on evaluating Test2VA's performance in generating task methods from 34 test cases across 8 different mobile applications. The success rate of Test2VA in generating task methods was 94.34%, with 50 out of 53 methods successfully executed. However, upon manual analysis, it was found that not all successful executions were of high quality. There were flaws categorized into 4 types. Type 1, incorrect mutable event. Type 2, unnecessary mutable event. Type 3, non-generality mutable event. And Type 4, success. Failures in the evaluation were attributed to 3 main reasons: unrecognized APIs and patterns, bad assertion design, and flaky test cases. In terms of mutable event detection, failures occurred due to unreasonable input values, low-quality base tests, and failed assertion modification. To mitigate threats to internal validity, such as potential mistakes in data processing and bugs in the implementation of Test2VA, the authors carefully double-checked all the code and data and used a diverse set of apps to cover a variety of testing scenarios. The discussion section highlights limitations of Test2VA, including its inability to handle system events like turning on notifications or turning off Wi-Fi, and its focus on click and input actions. The paper suggests that future work could extend Test2VA to include additional action types and broaden the scope of mutable event searching. The table on page 10 of the research paper presents the results of mutant detection for 8 real-world Android applications, showing the number of non-mutable events, correct detections, and time costs. These results demonstrate a 75.68% mutation detection rate, indicating that Test2VA provides a solid foundation for future improvements. To enhance the task logic, the authors propose considering the basic action as a macro event, rather than a single GUI event. This approach can simplify the event sequence and allow for more accurate representation of actions. The authors acknowledge that Test2VA does not currently utilize advanced AI techniques, but identify potential areas for improvement, such as using synthetic data generation to generate realistic zip codes. They believe that future AI integration will increase the accuracy and efficiency of Test2VA. The related work section discusses existing research on voice assistants, code extraction and mutation, and test reuse and migration. The authors highlight the limitations of current approaches, such as universal control and programming by demonstration, which focus on end-user support rather than developer support and rely on user-provided instructions. They also distinguish their approach from code mining and mutation testing techniques, which are not directly applicable to Test2VA. The conclusion summarizes the proposed approach of Test2VA, which reuses GUI test scripts for voice assistant feature development on mobile applications. The approach involves parsing and re-executing test scripts to extract task patterns and generate methods to support task execution. The results demonstrate the feasibility and potential of Test2VA, with a 75.68% mutation detection rate and the generation of 33 flawless methods. The research paper presents a novel framework for analyzing complex systems, integrating multiple methodologies to elucidate the intricate relationships between system components. This approach, termed hybrid multiscale analysis (HMA), combines the strengths of topological data analysis, network science, and machine learning to provide a comprehensive understanding of system behavior. HMA is grounded in the concept of topological feature extraction, which enables the identification of crucial system components and their interactions. The authors employ the Betty number, a topological invariant, to quantify the complexity of system topology. This metric is used to construct a multi-scale representation of the system, capturing both local and global properties. The framework is further augmented by incorporating network science techniques, which facilitate the analysis of system structure and dynamics. The authors utilize the Louvain algorithm for community detection, revealing the modular architecture of the system. This information is subsequently used to inform the machine learning component of HMA, which involves training a graph neural network to predict system behavior. The authors demonstrate the efficacy of HMA through a case study on a complex biological system, showcasing the framework's ability to uncover novel insights into system behavior and predict emergent phenomena. The results highlight the importance of considering multiple scales and perspectives when analyzing complex systems. Notably, the authors acknowledge the limitations of HMA, including its reliance on high-quality data and the need for further refinement to accommodate systems with non-uniform scales. Future work involves expanding the framework to accommodate these challenges and exploring its applicability to diverse domains. The research paper presents a comprehensive dataset of 54 distinct electroencephalography (EEG) biomarkers, each characterized by unique spectral and spatial features. These biomarkers are derived from a large-scale analysis of EEG recordings from 1,000 individuals, encompassing a wide range of cognitive and neurological disorders. The authors employ a data-driven approach, leveraging advanced machine learning algorithms to identify patterns and correlations within the EEG data. This methodology enables the identification of novel biomarkers that may not be apparent through traditional, hypothesis-driven methods. The 54 biomarkers are categorized into 6 distinct groups, based on their spectral characteristics, spatial distribution, and functional associations. These groups include biomarkers related to alpha, beta, and theta frequency bands, as well as those associated with cortical and subcortical brain regions. Notably, the authors demonstrate the utility of these biomarkers in distinguishing between different neurological conditions, including Alzheimer's disease, Parkinson's disease, and major depressive disorder. The results suggest that the biomarkers can serve as diagnostic tools, enabling early detection and personalized treatment of these disorders. The study's findings have significant implications for the development of precision medicine and personalized healthcare. Furthermore, the authors identify several avenues for future research, including the integration of EEG biomarkers with other neuroimaging modalities and the exploration of their potential applications in neurofeedback and brain-computer interfaces.